So today we're going to talk about really from a thermal standpoint. Day-to-day, RDH and myself, we're facade designers really. We deal with the building enclosure. We're building scientists by trade. But on a day-to-day basis, most of our projects deal with designing the skin. So a big chunk of that's keeping water out of our buildings, making them energy efficient and airtight. I'm going to leave that kind of stuff to the other guys maybe. I'm really going to talk about the thermal side of building enclosure design and building enclosure engineering, and talk about, in particular, what the impact of structure is. And so by the end, what I want to show you guys is that there are some pretty significant thermal impacts, benefits to using mass timber as compared to some other kind of non-combustible, traditional structural materials. So we'll go into a little bit of the science of that, and hopefully it won't hurt too much, but that's where we're heading. Again, you guys have probably read this already, so we'll skip over that. I have had some good fortune of working on some really interesting CLT projects over the years, mass timber projects. From a facade perspective, some of them are pretty basic. Some of them aren't that different than what we would do for a typical stick-built building or a concrete or steel building. This is a building in Vancouver. Doesn't look anything different from a facade perspective to what we might otherwise do. We have an air and water barrier in the exterior. We have a bunch of exterior insulation for thermal insulation, and we have a drained brick veneer on the exterior. One of the interesting things I think that we're really pushing the envelope with on mass timber buildings is one of the advantages of mass timber buildings from a structural perspective is the speed of erection, how quickly it can go up. So we're really starting to push the envelope a little bit on some of these kind of newer projects. And if the structure is going up this fast, how can we get the facade to go up equally as fast and maintain some of those advantages that we're gaining on the structural side? So this is the Wood Innovation Design Center, some projects you guys may be familiar with some small panelized facades. And certainly Brock Commons, if anyone's seen that, we were involved designing the facade system on this building. So these are kind of some of the projects in the mass timber variety that we've worked on over the years. So with that kind of background about what we do and where we are, this is kind of what we're going to talk about. We're going to talk about a little bit of science about thermal control in buildings. I want to show you guys how important details are, to the overall thermal performance of buildings. Sometimes very often we overlook them and think that the details don't matter, but it's not the case. And we'll talk about how mass timber really lends itself to some advantages there. All right. Overall energy usage of buildings, this is a graph. So this is Canada on the left. This is for housing, for residential buildings in particular. So the overall energy usage of the average home in Canada, I have a California graph, which is where I'm located currently on the right. So it's a little bit less energy usage in California, which kind of makes sense. It's a much more moderate climate compared to Canada. Heating and cooling loads in both climates, we could probably guess that Portland and Oregon might be somewhere in the middle, both geographically and from an overall energy usage perspective. The heating and cooling elements here, really significant in cold climates and still pretty significant in even pretty moderate climates like California, really sizable chunks of the overall energy usage of buildings. And the building enclosure, how we insulate them, how we control thermal losses through the building enclosure drives how big these numbers are. So if we do a better job insulating our building enclosures, we can really drop these numbers down. I think you're going to talk a little bit about passive house, and one of the serious goals of passive house is really cutting down the sliver of that blue bar. All right? So some really background science, maybe high school physics or maybe some thermodynamics class that you took in college. From a material property perspective, you can look it up in an engineering textbook anywhere. Steel is a really good conductor of heat. Wood is a reasonable insulator. Material properties, if we talk about units of whether they're be IP or SI, round numbers here. Steel has a thermal conductivity of approximately 60 in SI units. Wood, by comparison, is 600 times less than that. So just from a material perspective only, we can, by looking at these numbers in a table out of an engineering textbook, we can really understand that wood is actually a pretty good insulator. It's why we make frying pans out of steel and we don't make frying pans out of wood, right? So intuitively, we kind of get that. We appreciate that. But it really does make a big difference when we start building our buildings out of these things. So beyond the material level, when we start looking at assemblies, we can look at the overall thermal performance of an assembly, and again, this is pretty background science, so I apologize if I'm going too slow. But in one dimension, we can add up the thermal resistances of various layers in our assembly. We can add the resistance of our interior drywall, add the thermal resistance of our bad insulation or our rigid insulation on the exterior. We can add those up and get an R value for our assembly, or overall resistance to heat flow. In 2 and 3 dimensions, which was most of what our energy codes require of us, we have to account for thermal bridging through framing members, structural members, things like that. So this is where we commonly see one of the benefits thermally of using wood frame construction, right? So pretty common wood frame assembly, we might do a 2x6 wall with studs at 16 inches on center, put bad insulation. And because wood is a decent insulator in and of itself, about R1 per inch, we get overall pretty good thermal performance of the overall assembly when we look at it in 2 dimensions. Not quite the same for steel, again, because steel is such a good conductor of heat. So graphically, we can look at that. The bottom scale here is how much framing we have within the wall. So a common framing factor is in the order of 25%. And depending on our structural material and how much of that structural material we have in our wall, our overall effective resistance to heat flow, or R value, drops down pretty significantly, pretty quickly, right? So typical 2x6 wall, effectively, if we put an R21 bat in it, we'll get something in the range of R15 or R16 effectively. Our steel stud wall with the same amount of insulation, R21, will get us down into the R6, R7 range, something like that. So again, most of us probably appreciate this. When we switch to mass timber from light timber buildings, what's the framing factor of a mass timber building, a wall that uses mass timber? 100%, right? It's all wood, right? We don't have sticks at 16 inches on center, it's all wood. So this wood stud line goes down and gets to 100% if we continue that graph out to the right. And CLT, or other mass timber panels that are continuous, have a framing factor of 100%, are actually reasonably good insulators. So a 6-inch piece of CLT gets us about R7.5. Round numbers, wood is about R1 per inch, as we talked about in the last slide. So even when we have continuous sheets of wood, there's actually a lot of inherent insulation in there that helps us from an overall assembly perspective. So if we compare materials side by side, whether it's a steel stud wall or a CLT wall, in both cases, in most climates, we're supplementing the insulation that may exist between the structural elements or might be provided by the CLT panel itself. We're supplementing that with some insulation on the outside. And if we look at these things in 2 dimensions, we can design these assemblies to have the exact same overall resistance to heat flow, right? We can vary the thickness of this exterior insulation so that the R value of this assembly and the R value of this assembly is exactly the same. Now, depending on how thick the studs are and how thick the interior insulation between the studs is, we may have to vary the insulation levels on the exterior to get these things to look the same from a thermal perspective in 2D. But we can do that, and pretty simple modeling tools we can use to do that. But do they really perform the same in real life? Not sure. All right. I'm going to try to convince you that the answer is no. So this is a guideline document out there about thermal bridging, kind of an industry guide. It's a really, really good resource if anyone's doing some kind of detailed analysis about thermal bridging, the Building Envelope Thermal Bridging Guide. Just a quote out of that book. Our buildings aren't as efficient as we think they are, one. Our facades aren't as efficient as we think they are. And for typical cases, 2 times to 4 times more heat loss than expected by simple 2-dimensional models. There's a whole bunch of things happening in 3 dimensions that looking at an assembly like this doesn't take into account. Okay? What does this picture mean to anybody? Any thoughts? Curtain wall on a steel or concrete building, doesn't matter. But we can see dew on the outside of the curtain wall spandrel panel right there in the middle of the panel, right? Around the outside of the panel, no dew. So what we're seeing here is thermal bridging through the perimeter of the spandrel panel. There's a lot of insulation in the middle of the panel that's very continuous. There's no steel members or anything like that poking through it. But we have aluminum mullions from the curtain wall bypassing that insulation around the edges, and there's a whole bunch of heat flow, a ring of heat flow around the perimeter of the spandrel unit. So we could put R20 insulation, for instance, inside the middle of that spandrel panel, and when we look at it in more than a single section cut, and we account for the thermal losses flanking around the perimeter, that very commonly goes down into the range of R5 to R8. Cuts it well more than in half, right? So the reality of buildings is that they're not just a combination of 2D elements stuck together like maybe our idealized energy models think they are, right? So we might have this idealized box where we have an area of a wall section that has an R value, an area of a window section that has a specific R value, and we combine them together. The reality is that there's a bunch of thermal losses that happen across the interfaces, okay? So, numerically, very quickly, so don't let your eyes go across here. It's pretty simple math. Heat flow through an assembly Q is equal to the heat loss through the actual assembly itself, and you add in the heat loss that you lose through all the linear interfaces and the point interfaces between assemblies that you're thinking about. So the assembly is what you look at in 2 dimensions. You might calculate the R value, an effective R value of a wall assembly with studs in it and insulation, and you multiply that by the area of that assembly, and ultimately you multiply it by the change in temperature between in and out. And for all those other details that happen at either linear interfaces or at point interfaces, you can actually add in the heat loss through those interfaces, much like the linear perimeter maybe of a spandrel panel, and you can multiply those by the linear length that detail exists, or by the number of those point penetrations that exist. All right, so you start adding those things together, you get the total heat loss for the building. So those linear interface details, these psi values that I'm talking about, interfaces, that linear transmittance that happens where 2 things come together, can be really, really significant. And how we detail our assemblies really, really matters. So if we have a perfect detail thermally that we can't do in real life because it's just concrete and insulation in this case, if we have a perfect detail where we line up our window thermal break and our IGU perfectly with the insulation layer, again, not practical in real life, we can get a really low psi value, okay? Very minimal heat loss through the interface between the concrete wall and the window. Now, maybe we want to recess that window a bit into the concrete opening, right? So again, this might be something we would commonly do architecturally or aesthetically, but now because this insulation here isn't lined up with the insulative portion of the window, that thermal flanking that happens, that heat loss that's going to basically bypass the insulation of these 2 assemblies across that path there, shoots the linear transmittance of this detail up by huge percentages, okay? Same thing can happen at parapets and a billion other details that happen around our buildings. If we wrap our insulation around our parapet assembly, we can get really low linear transmittance values from the parapet. We leave that parapet open, it goes up by 10-fold. Okay? Really, again, really significant differences with pretty subtle changes in how we're wrapping things in insulation. The details matter a lot. So if we look at, these numbers may not mean anything to us. What do they mean to the overall energy usage of the building? So let's go back to our rectangular box, really simple building, 30 feet square, 3 floors, 1,000 square foot of floor, 1,000 square feet of roof, 1,000 square feet of floor. Just really simple numbers. You can do the math. We have 960 lineal feet of window perimeters. We're going to have 120 feet or so of parapet interface and things like that. So if we do some really simple math, that formula that I had up there, UA delta T, calculate that Q, that heat flow. So we add the walls, we take a U value of the walls, we multiply by the area of the walls, we come up with UA, and you add those up at the bottom, we get a number of 795, okay? Number doesn't mean anything in real life, but as a comparative measure. So what if we put in those psi values from the window perimeter interface and the parapet perimeter interface that I talked about in those last details? Those are really, really significant numbers in the grand scheme of things here. Our total heat loss through our building, by taking into account 2 details that our energy models typically wouldn't pick up at all if we did them in common methods, shoots our heat loss through our building up by 25%. How many other details exist on the building that we haven't thought about, right? You could lengthen this list here pretty quickly, and you would realize that the details very quickly can add up to the heat loss through the window interface is more than the heat loss through the entire wall area that's 2,400 square feet. Okay? The details matter a lot. If we did those perfect interface details that we talked about with the really low linear transmittance values that probably aren't practical in real life because we physically can't align things perfectly all the time because of constraints with architecture and things, we can do pretty well, and we can get these numbers down really low, but the details matter a lot. We can go from something, increasing the baseline over 25%, 30% maybe, to not moving the needle much at all if we think about the details properly. Mass timber, these interface details in mass timber, what's the difference? Like I think I alluded to, the perfect details that may exist that give us really good values for linear transmittance at interfaces are hard to achieve in real life. There's going to be some trade-offs we have to make. We need to hold stuff onto our building. We have attachment considerations, right? We need to deal with air and water. We have metal flashings and things like that that can really compromise getting that a perfect alignment of our insulation between assemblies. The benefit of mass timber here is that because you have decent thermal insulation in your structure itself, even if your linear interface detail isn't perfect and you have some bridging of your insulation at interfaces, the actual thermal resistance of your structure that's going to be continuous through that detail can really benefit you in the long run by lowering the linear transmittance values across those interface details. Okay? So two identical details, same R value in the center of the wall. If you put them in an energy model with a U value in a cross-sectional area, these things would look the same in 2 dimensions when you can combine them. Same window, and just by changing the structural material from steel stud and bat to CLT, for the steel stud condition, we've increased that thermal transmittance of this interface condition by 50% almost. Okay? Pretty significant. And the more we insulate the walls and the better the windows are, that number goes up higher and higher and higher. The interface detail becomes more and more important as we get more insulative assemblies. Concrete slabs, right? They get a lot of bad press potentially if you start looking at the science of how much the thermal bridging is through concrete slabs that poke through insulated walls. So if we, for interest's sake, if we had an R20 wall here, effective, taking into account thermal bridging through the studs and all those things, continuous insulation on the outside maybe, and we had a wall that was R20, when we slice it through with a concrete slab like that, that R20 goes down to about R10 overall for the building. Right? So the difference of using mass timber products or other types of products that are more insulative at these interface details, we can drastically reduce the the linear transmittance across these interface details. And again, very often these are things we just overlook in energy models and forget about. So even if our energy model says that these two buildings are the same, the reality in real life is a whole bunch of these details that we've overlooked in preparation of our energy models, actually we save a lot of energy by doing that at timber. Okay? Through-wall flashing details is kind of something we're pretty familiar to seeing, certainly in the Pacific Northwest. We maybe have a rain screen wall and we have a flashing at a floor line to divert water back to the exterior. So the reality of just putting this in, slicing through your insulation layer with a piece of sheet metal, interrupting that insulation and connecting that piece of sheet metal to really conductive heat, concrete and steel at these interfaces drastically jumps up the linear transmittance of those details. It's not zero with CLT, right? There's always going to be some thermal losses that happen at these details where our insulation is discontinued for a little bit. But huge significant differences just because of structural material choice. Okay? One of the major last effects that we do see with CLT buildings, mass timber buildings in particular, is the effect of thermal mass. So this is a graph right out of the CLT handbook for those who are familiar with it. There's a building enclosure section of the CLT handbook that we authored, and this graphic is right out of there with a whole bunch of more description in the background if you're interested. But there is thermal mass to CLT. CLT can absorb heat and store it for a while. It can bulk up and basically store heat and then release it slowly over time. So if you compare that to light gauge framing, steel stud construction, for instance, which is common, the effect that CLT, the storage of that heat that it can store and release it slowly over time, has on overall energy efficiency, so energy savings of CLT compared to light framing, it varies by climate, it varies by a whole bunch of variables. But when we're talking exterior insulated assemblies in comparable type assemblies, just altering the structural material, we're talking in the range in many climates of somewhere from 5 to 20+% energy savings overall just because of thermal mass and no other difference. So again, there's lots of research and lots of background about this in the CLT guideline for those that are interested. But again, combine the thermal mass effects with all these details that are just become naturally simpler to do better thermally with mass timber, the thermal performance of these buildings is much further ahead than it would otherwise be with some other structural materials. All right, so wrapping this all up, as a structural material, wood's a good insulator. It's one of the nice things. There's a lot of good properties of wood, carbon sequestration, the fact that it's renewable and we can grow it. From a building science, from a building enclosure perspective, the fact that our structure is a pretty good insulator at the same time is really nice, and it helps us add interface details in particular. So not only it may thin down the amount of insulation we need on the exterior of our structures to get equivalent R values in the center of the wall, when we get to interface details, window perimeters, parapets, exposed floor lines, things like that, really significant savings there from overall heat loss and overall energy usage of our buildings as a result of that insulative structural material. So those chi values, if you go to that thermal bridging guide that I mentioned earlier, there's tables and appendices in the back talking about chi values, linear transmittance values, how much heat happens at linear details. Those are just naturally lower when you have a reasonably insulative structural material in behind. Okay? So that's it. On to the next one.